This talk is called Beyond the Cradle, Structural Foundations for the First Step of Human Civilization on the Moon. Rabbit pounding rice cake on the moon. It is the old Korean folktale about the rabbit in the moon, a nice bridge between myth and the real engineering we're about to do up there. Recent news: SpaceX Falcon 9 upper stage actually impacted the moon, and Korea's own KPLO orbiter captured before and after images of the crater. Let's ground this in real numbers. Apollo 8 in 1968 proved lunar navigation, 6 days, 3 hours round trip. Artemis 2, launching this year, retests those systems in deep space with modern hardware. Same 350,000 kilometers distance, same physics, 6 decades of technology apart. Here's the real unlock. Launch cost per kilogram. From Saturn V $6,000 to Shuttle $50,000 to Falcon 9 $200 to Starship, we've gone from tens of thousands of dollars per kilogram to what SpaceX projects as low hundreds. That cost curve is what turns lunar structures from science fiction into a reality. NASA has laid out a phased $20 billion plan: secure surface access now, establish base operating capability by 2029, and semi-permanent crew presence starting 2032. That's not a 100-year horizon. That's a career-length horizon for people in this room. On Earth, our code framework is simple: gravity, wind, seismic loads, wood, concrete, steel, safety-based design methods. Keep this in your head. We're about to blow it up. This is a conceptual illustration of what a lunar habitat cluster might look like: modular geodesic domes, connected, partially buried. It's speculative, but the structural logic behind it is not. Gravity is the first variable that changes everything. Moon gravity is about 1/6 of Earth's. Mars is about 38%. No atmosphere means no wind on the moon. And Mars has both wind and Marsquakes. Every planet rewrites your load combinations. So here's the framework for the rest of this talk. 8 forces that replace gravity, wind, and seismic as the governing design drivers on the moon. Vacuum and internal pressure, thermal extremes, radiation, micrometeorites, abrasive regolith dust, low gravity, foundation, bearing behavior, and limited maintenance access. Bringing it together into structural form, domes are most efficient for interior pressurization. Cylinders are easiest to manufacture. Buried habitats give radiation and micrometeorite protection. Lava tubes add stable temperature for free, and inflatable plus regolith hybrids optimize for shipping cost and airtightness. The right answer is usually a combination, not one pure form. This is where it gets personal. My own concept sketch for a deployable geodesic habitat developed for an Aerospace Forum. Geodesic hexagonal shell for structural efficiency, uniform load distribution, a deployable truss frame for compact transport, and an attachable cylindrical module for airlock and utilities. And this is where structural engineering actually starts, running ribbed, geodesic, Schwedler, and lamella dome forms through SAP 2000 to compare deflection and force distribution. The geometry is elegant, but it still has to pass structural analysis like anything else we design. To validate the joinery and panelization, we laser cut a physical 3D geodesic dome model in 1/8 inch basswood, tab slot connections, the same kind of DFMA thinking we'd apply to a real deployable structure. Here's the finished model, a tangible proof of concept for how a geodesic lattice actually assembles. I'll close the visuals with this. AI Space Factory's Martia concept, a 3D printed vertical habitat for Mars. Different planet, same underlying question. How do you build a pressure vessel that can survive an environment that wants to destroy it? 3 things to leave with. 1. We're in a new space race. Artemis 2 this year and NASA's $20 billion phased moon base plan make this alive. Near-term discipline, not science fiction. 2. The moon fundamentally changes the load case. Internal pressure, vacuum, plus or minus 300 degrees Celsius swings, radiation, and micrometeorites replace gravity, wind, and seismic as the governing forces. 3. The path there runs through robotics and 3D printing, domes or cylinders, shielded with in situ regolith, built by machines before any human sets foot inside. From tall buildings on Earth to habitats on the moon, the structural questions don't go away, they just change shape. Thank you.